Welcome to the lecture on evaluation part 1. Part of the material presented in this lecture is taken from the following book. Transcription and interpretation errors are responsibility of the lecturer. In this lecture, the following concepts will be introduced: interesting-uninteresting association rule, lift, interest factor, correlation analysis, and finally IS measure. Once you have generated a set of patterns which are potentially useful for the director of the mini-market, you must rank them in order of interestingness. What is trash for you could be gold for the director of the mini-market or vice versa. It is important to establish a set of well-accepted criteria for evaluating the quality of the association patterns. In the specialized literature, usually two sets of criteria are presented: criteria based on statistical arguments and criteria based on subjective arguments. We start by focusing our attention to the set of criteria based on statistical arguments. This set of criteria search for patterns involving a set of mutually independent items and on patterns covering very few transactions. Indeed, such type of patterns are known to be uninteresting, and this is because they may capture spurious relationships in the data, so this type of patterns must be removed. In particular, they can be eliminated by applying an objective interestingness measure, which typically uses statistics derived from data to determine whether a pattern is interesting or not. Examples of objective interestingness measures are the following: support, confidence, and correlation. Shifting the attention to the set of criteria based on subjective arguments, we have the following. A pattern is considered subjective uninteresting unless it reveals unexpected information about the data or provides useful knowledge that can lead to profitable actions. To clarify this aspect, we exploit the following example. We have that butter is associated with bread. This rule is known to be uninteresting, despite having high support and confidence, because the relationship represented by the rule may seem rather obvious. On the other side, we have that the association diapers beer is known to be an interesting one, because it is unexpected and may suggest cross-selling opportunity for retailers. So, in particular, to specify what is uninteresting and what is interesting requires the prior knowledge or the domain knowledge. However, incorporating subjective knowledge into pattern evaluation is a difficult task because it requires a considerable amount of prior information from the domain experts. We now introduce the concept of objective interestingness measure. An objective interestingness measure is a data-driven approach for evaluating the quality of association patterns. It is domain independent and requires minimal input from the users, typically just the value of a threshold parameter. Furthermore, it is computed based on the frequency counts tabulated in a contingency table, so a table of the following form, where we have that A has the following meaning: item A is present in the transaction, while not A has the following meaning: item A is not present in the transaction. The elements of the contingency table can be introduced as follows. In particular, F10 has the following meaning: it is the number of transactions where item A is present, while item B is not present. So in particular, F11 is the number of transactions where both items A and B are present. F10 is the number of transactions where the item A is present and the item B is not present. The same applies to the other elements of the contingency table. However, the elements that are associated with F1 plus, F0 plus, F plus 1 and F plus 0 have a particular meaning. In particular, F1 plus has the following meaning. It is the support count for the item A, while F plus 1 is the support count for the item B. And we remind that capital N is the number of transactions of the transaction dataset. We now analyze the following situation. Suppose the director of the mini-market is interested in analyzing the relationship between people who drink tea and coffee. Then, the following contingency table is computed from the available transactions, so using the transactions dataset. This is the contingency table. In particular, the transactions dataset consists of 1,000 transactions. And we have that the item T is associated with item A of the previous contingency table, while the item coffee is associated with the item B of the previous contingency table. We can read from the counts of this contingency table the following facts. First, we have that 150 transactions of the 1000 forming the transaction database are such that the items tea and coffee co-occurred, while we have 50 transactions where the item tea was included while the item coffee was not included. Then the information given in this table can be used to evaluate the following association rule. People who drink tea tend also to drink coffee. We now analyze this rule by first computing its support. In particular, to compute the support of this rule, we first need to compute the support count, so the number of transactions where both tea and coffee occurred. This value can be obtained from the contingency table, and it is equal to 150. Now, if we divide the support count by the total number of transactions, which is equal to 1000, we obtain the support of the rule of this rule, which is equal to 15%. We close the analysis of this association rule by computing its confidence. The confidence of this association rule is defined to be the ratio of the number of transactions where both the items tea and coffee are present, are included, to the support count for the item tea. So from the contingency table we compute the following ratio: 150 divided by 200. Then we obtain that the confidence for this association rule is equal to 75%. At a first glance, it may appear that people who drink tea also tend to drink coffee. However, we ask ourselves, how can we check whether this is true or false? So how can we check whether this rule is interesting or not? The answer to the previous questions, or whether the association rule that we have extracted is interesting or not, is obtained by further analyzing the content of the contingency table. In particular, from this contingency table, we can conclude that the fraction of people who drink coffee, regardless of whether they drink tea, is equal to 80%. Indeed, it is equal to the support count of the item coffee to the number of transactions of the transaction database, so 1000, and this is equal to 0.8, while the fraction of tea drinkers who drink coffee is only equal to 75%. Indeed, it is equal to 150 divided by 200. So it seems that this association rule is not interesting. Indeed, if we know that a given person is a tea drinker, then the confidence that he or she also drink coffee is equal to 75%, while regardless of whether the person drinks tea, the probability that he or she drinks coffee is equal to 80%, so it is greater than the confidence of this rule. On the basis of what we have just observed, we conclude that judging the interestingness of an association rule using confidence can be misleading. Indeed, this association rule is misleading despite its high confidence value, which is equal to 75%. But which is the reason why confidence can be misleading to judge the interestingness of an association rule? The reason is the following: that the confidence ignores the support of the item set in the rule consequent. So it ignores the support of coffee in this case. Well, we conclude this lecture by introducing and describing some evaluation measures. We start by introducing the interest factor, which addresses the problem of confidence, or in other terms, the issue of ignoring the support of the item set appearing in the rule consequent. To introduce interest factor, we first need to introduce the concept of lift of an association rule. Lift of an association rule A implies B is defined as shown. In particular, lift is the ratio of the rule confidence to the support of the consequent. In particular, for binary attributes, the lift is equivalent to another objective measure called interest factor, which is formally defined as follows. Interest factor between A and B is equal to the support of A and B divided by the product of the support of A and the support of B. It can be also translated to the ratio between capital N F11 to F1 plus times F plus 1. In particular, interest factor compares the frequency of a pattern against a baseline frequency computed under the statistical independence assumption. In particular, we have that the interest factor AB is equal to 1 if A and B are independent, while it is greater than 1 if A and B are positively associated, and it is equal, or in particular, it is smaller than 1 if A and B are negatively associated. In particular, we have that the elements F11, F1 plus, and F plus 1 are those highlighted in this contingency table. It is worthwhile to mention that interest factor typically is not used to in the particular area of text mining to evaluate association between pair of words because it can be extremely misleading. The second interestingness measure we introduce is correlation analysis. It analyzes relationships between a pair of attributes. In particular, continuous attributes are analyzed using Pearson's correlation coefficient. Correlation for binary attributes is measured using the phi coefficient, which is defined as follows. In particular, the phi coefficient ranges from -1 to +1. If the items are statistically independent, then its value is equal to 0. This means that phi is equal to 0. It is more suitable for analyzing symmetric binary attributes, so those cases where the presence and the absence of the item is equally relevant.
The third and last evaluation measures we introduced in this lecture is the IS measure. It allows to handle asymmetric binary attributes, and it is formally defined as follows. IS of AB is equal to the square root of IAB times S of AB, where I of AB is the interest factor of the pair A and B, while S of AB is the support of A and B. This can be rewritten as follows, as the ratio of the support of A and B to the square root of the product of the support of A times the support of B. It is large when the interest factor and support of the pattern are large. It is worthwhile to mention that the IS measure can be used in text mining to evaluate association between pair of words. In the case where A and B are independent, we have the following. The IS measure between A and B can be written by definition as the ratio of the support of AB to the square root of the product of the support of A times the support of B. However, due to the hypothesis or assumption of independence between A and B, the numerator SAB can be written as the product of SA, the support of A, times the support of B. Then this equation simplifies to the square root of SA times SB, so the product of the support of A and the support of B. The IS measure shares a similar problem as the confidence measure. In particular, the value of the measure can be quite large, even for uncorrelated and negatively correlated patterns.